Download this code from codegive.com, link in the description below. OK, let's dive deep into creating a reliable delay loop in Starmade's Logic 2.0 system, specifically focusing on how to detect and handle errors that can break these loops. Delay loops are essential for timing events, managing resource flow, and orchestrating complex sequences within your ships or stations. However, they are vulnerable to issues like power loss, component failure, or unexpected game behavior. We'll explore strategies for building robust loops that can detect these disruptions and recover gracefully. Understanding the basics, the traditional delay loop. Before we get into error detection, let's refresh ourselves on how a basic delay loop works in Logic 2.0. A delay loop essentially holds execution for a set period before continuing. This is achieved by storing a timestamp, a value representing in-game time, and repeatedly checking if the current time has exceeded that timestamp by a certain delta. Here's a simple, but potentially problematic delay loop implementation. Explanation asterisk. 1 variables asterisk. Asterisk delay start time, stores the game tick number when the delay started. Asterisk delay duration, stores the desired length of the delay in ticks. Asterisk loop status, tracks whether the delay loop is actively running. Asterisk current time, stores the current game time, acquired from time. 2 time, asterisk this is the fundamental function. It returns the current game tick. You rely on this to measure elapsed time. 3 initialization asterisk. Asterisk the loop starts when loop status is 0. Asterisk delay start time is set to the current time. Asterisk loop status is set to 1 to indicate the loop is active. 4 delay check asterisk. Asterisk if loop status is 1, the code checks if the difference between the current time and delay start time is greater than or equal to delay duration. Asterisk if the delay has passed, loop status is set back to 0, and the delayed code is executed. 2. The problem, why the naive loop fails and needs error detection. The basic delay loop above has critical flaws. It's vulnerable to disruptions that will cause it to either 1. Hang indefinitely asterisk if the system loses power during the delay, current time will stop updating. When power is restored, the delay condition, current time, delay start time equals delay duration, might never be true because delay start time remains stuck at an old value. The loop gets stuck in the else block, continually checking a condition that will never be met. This essentially breaks your system. 2. Trigger immediately asterisk if current time somehow rolls back to a value earlier than delay start time, the condition becomes trivially true, triggering the delayed code far too soon, or even repeatedly in a single tick. This can cause unpredictable behavior, especially if you are controlling devices. 3. Variable reset/overwrite asterisk if your ship's block gets reloaded by the server, example caused by warping or exiting and returning to the area, the static int values, including delay start time, can be reset, causing unintended behavior. 3. Error detection and handling strategies. Here are several strategies to detect and address the problems outlined above, along with code examples. A. Time jump detection, rollback detection. This method specifically detects when the current time goes backwards, jumps to an earlier time, which could be due to unforeseen errors or strange server behavior. Explanation asterisk. Asterisk last time, stores the current time value from the previous execution of the logic block. Asterisk we compare the current time to last time. If current time is less than last time, it means time has gone backwards, signaling a serious error. Asterisk the error handling logic. Asterisk prints an error message. Asterisk resets delay start time and loop status to ensure the loop starts over cleanly. Crucially it provides placeholders for more robust error handling. Printing is only useful for debugging. You need actions that actively prevent further errors or alert the user. B. Timeout protection, power loss detection. This addresses the most common issue, power loss. We assume the logic block is supposed to be executing at least somewhat regularly, example every tick. If too much time passes without the logic executing, we assume something went wrong. Explanation asterisk. Asterisk last execution time, stores the last time the logic block successfully completed an execution cycle. Asterisk timeout threshold, the maximum allowed time, in ticks, between executions. Adjust this value based on how frequently your logic block is expected to run. Asterisk the timeout check. Asterisk the loop only attempts to run after the first execution of the code, so the last execution time needs to be initialized first to avoid an immediate timeout. Last execution time equals 0. Asterisk if the difference between the current time and last execution time exceeds the timeout threshold, a timeout error is triggered. Asterisk the same error handling logic as before is applied, reset the loop, print an error, and consider more robust responses. See combined error detection, a more robust delay loop. Now, let's combine these error detection strategies into a single, more resilient delay loop. This is the code you should start with as a template for your delay loops. Key improvements asterisk. Asterisk combined error detection asterisk it now includes both time rollback and timeout detection. Asterisk error flags asterisk time rollback detected and timeout detected flags are introduced. These are crucial. Once an error is detected, these flags prevent the loop from starting until you explicitly clear the error condition. This stops the loop from constantly restarting and erroring out in quick succession. Asterisk explicit error handling placeholder asterisk the else block now has a clear section for you to add your own error handling code. Asterisk resetting error flags, after your custom error handling, the error flags are reset. This allows the loop to attempt to function normally on the next tick if the underlying cause of the error has been resolved. The alternative would be a permanently disabled loop. Asterisk constants, using constants helps readability and makes the code easier to maintain. 4. Advanced error handling strategies. The previous code provides a good foundation. Here's how you can make the error handling even more robust and practical. 1. Logging to memory banks asterisk. Asterisk use memory banks to persistently record error events. This allows you to analyze errors even after they occur. Asterisk store relevant data, example error type, timestamps, system state, in the memory bank. 2. Safe mode activation asterisk. Asterisk create a safe mode state where your system suspends critical operations and enters a safe configuration. Asterisk for example, you might disable weapon systems, throttle down engines, or shut down resource-intensive processes. Asterisk use a memory bank to store the safe mode status so that it persists across logic block reloads. 3. Error retries with exponential backoff asterisk. Asterisk instead of immediately resetting the loop, attempt to retry it after a short delay. Asterisk if the error persists, increase the delay between retries. This is called exponential backoff. This can help your system recover from transient errors. Asterisk limit the number of retry attempts to prevent the system from getting stuck in an infinite loop. 4. User notification asterisk. Asterisk use holographic projectors or other visual displays to inform the player about errors that have occurred. Asterisk this helps players quickly diagnose and resolve issues. V. Practical considerations and tuning. Timeout threshold experiment to find the optimal timeout threshold value. Too low, and you'll get false positives, timeouts when the system is actually working. Too high, and you might miss genuine power loss events. Consider the expected execution frequency of your logic block and the potential for brief lag spikes. Memory bank usage. Avoid excessive reading and writing to memory banks, as these operations can be relatively slow. Optimize your logic to minimize memory bank accesses. Game tick speed. The game tick rate can vary slightly depending on server load. Take this into account when setting delay duration and timeout threshold values. 6. Complete example: combined error detection with memory bank logging. Here's a complete example, incorporating both error detection and logging to a memory bank. 7. Debugging tips. Print statements. Use print liberally during development to monitor variable values and execution flow. These can be invaluable for diagnosing errors. Logic debugger. The in-game logic debugger is useful for stepping through code execution and inspecting variable values in real time. Simplify. Start with a simple delay loop and gradually add error detection and handling features. This makes it easier to isolate and fix problems. Test thoroughly. Simulate power loss events, time jumps, if possible, and other potential error conditions to verify that your error handling logic is working correctly. 8. Conclusion. Building reliable delay loops in Starmade's Logic 2.0 requires careful attention to error detection and handling. By implementing strategies like time jump detection, timeout protection, and robust error responses, you can create systems that are more resilient to disruptions and can recover gracefully from unexpected events. Remember to tailor your error handling logic to the specific needs of your system and to test your code thoroughly. Good luck.